We're now ready to begin working a problem involving the equivalence point. At the equivalence point, the moles of base added is equal to the moles of acid you originally had. From our previous problem, we knew that we had 2.5 times 10 to the minus third moles of our acetic acid, which I'll represent as AA. We've now gotten to a point where we've added 25 milliliters of our base, which was 0.1 molar, which means we have 0.01 moles of our sodium hydroxide for every 1 liter or 1,000 milliliters. And so we are confirming we do have identical number of moles of both acid and base. Because the titration involved sodium hydroxide reacting with our organic acid, acetic acid, and from the balanced equation we know that it takes one sodium hydroxide to react with one acetate, and when we do so we get one acetate ion for every acetic acid we react, or one sodium hydroxide we react. So at the equivalence point, we no longer have any sodium hydroxide. That is, we just take an initial point of view. We had 2.5 times 10 to the minus third moles of sodium hydroxide. We had 2.5 times 10 to the negative third moles of acetic acid. We didn't have any of these. We let the reaction go, and so at the end, we have no sodium hydroxide, we have no acetic acid. We've created 2.5 times 10 to the minus third moles of everything here. Of sodium, of acetate, and water. So we're in a situation now where we no longer have acetic acid available to react. Well, how are we going to find the pH? Well, we know that the acetate ion was the conjugate base of acetic acid. And we know that conjugate bases are capable of reacting with water in that we can take away a proton to reform our original material here. In this case, it's acetic acid. When we do so, when we remake that acetic acid, we strip off a hydrogen from water, leaving us a hydroxide ion. Well, since we have a hydroxide ion, this reaction is now classified as being a Kb. The equilibrium constant here is defined by the hydroxide. So we need an equilibrium constant that references the alkalinity or basic light conditions of the solution. Well, I didn't have the Kb value given to us in this problem. So how am I going to find it? Well, what you need to do is you need to recall that the product of acid and base dissociation constants equals the water autoionization constant, which is 10 to the minus 14th at 25 degrees C. Ka was 1.8 times 10 to the minus 5th, which means with a little algebra, we can figure out or determine that the Kb value is 5.6 times 10 to the minus 10th. So there we go, we've got Kb. Now, how do we figure out the pH? Well, we're going to have to go through and do an ice table. So I'm just going to quickly rewrite this equation so we can do an ice table under it. So we've got acetate, we've got water, we've got our acetic acid, and we've got our hydroxide ion. Our initial state, well, water we don't care about. Acetic acid, well, at the equivalence point, there is no acetic acid, so that's 0. Hydroxide, we're going to go ahead and treat that like being 0. And that we had 2.5 times 10 to the minus third moles of our acetate ion in solution. But we can't use moles in ice table. We have to use molarity. Well, we know the moles, so we just need to know the volume that this acetate ion occupies. Well, we started off with 25 milliliters of acetic acid. We added 25 milliliters of our sodium hydroxide, so we now have a grand total of 50 milliliters. So I'm going to take this number of moles and divide it by 50 milliliters, or 0.05 liters. So here we go. Let's figure out what that molarity is. 10 to the 2.5 times 10 to the minus third divided by 0.05. That gives me an initial concentration of 0.05 molar. So we're going to scratch this all out. Still have a 0 molar solution of acetic acid and a 0 molar solution of hydroxide. We now allow the change to happen. In this case, it's going to be fairly straightforward. We know the reactant side is going to go down. How do we know that? We know that because there is no product. And in order to get to equilibrium, we can't have any concentration with a value of 0 at equilibrium. So at equilibrium, I have 0.05 minus x, and x for the two products. We're ready for our equilibrium expression. So here we go. Kb equals our products. Our acetic acid times our hydroxide at equilibrium all over our acetic acid concentration. Over our acetate concentration. Kb we said was 5.6 times 10 to the minus 10th. At equilibrium, acetic acid is X, hydroxide is X, and the acetate ion is 0.05 minus X. Well, this looks like a quadratic, so I'm going to take a gamble and try and use my 5% rule to see if I can avoid using the quadratic. So with the 5% rule, go ahead and ignore this minus X term. We're going to take a guess that X is so small it's not going to really change that concentration. And so what we can do is take 5.6 times 10 to the minus 10th times 0.05 equals x squared. And let's just work that out real quickly. So 2.8 times 10 to the minus 11th is equal to x squared. And we find that x is equal to 5.29 times 10 to the minus 6. So this is the same as the OH minus concentration. Well, to get to pH, we have to go through POH. So what we do to find POH, that's just the negative log of our OH molarity, in this case 5.29 times 10 to the minus 6. And we find the POH is equal to 5.27. Now, should I have worried about this value and the 5% rule? Well, the answer is no. And the reason is, if we check to see the amount of error this value introduces, 5.29 times 10 to the minus 6 divided by the 0.05, here, that's what we always reference, it's the number we get it off of, times 100, we find that the amount of error is less than 0.1%. So it was an okay assumption. So we can move forward. So using the POH, we know pH plus POH equals 14. 14 minus our POH is going to be equal to 8.72. 14 minus 5.27. Oops, sorry. Yeah. Which we find is equal to 8.72. So at the equivalence point, we've got a pH of 8.72. It's a weak acid, and we know weak acids at the equivalence point have pHs greater than 7. So this seems to fit in with what we know.